So we're going to begin graphing rational functions. So first of all, what is a rational function? A rational function is when you're simply dividing two functions. And keep in mind that because your denominator can't equal 0, one of your functions, so the q of x, which is our denominator, cannot be 0. Also, just a reminder, because this is a recording, you can pause and rewind at any time to capture any special notes. So the first thing we're going to talk about is finding the intercepts. Finding the intercepts. The first thing you should note is that an intercept, when we're talking about an x-intercept, that comes from the numerator. So for this first example, you're going to begin first by factoring the numerator and the denominator. So I'm going to factor both. Well, actually, I'm not going to factor the denominator because I don't need to. So when I factor the numerator, I need two numbers that multiply to be -8 and add to -2. Feel free to pause the video to see if you can find those numbers on your own. So I get x minus 4 and x plus 2. So now to find my x-intercepts, I am going to set both of those equal to 0, starting with the x minus 4. And whenever we're writing an intercept, it's good practice to always write it as an ordered pair. So I'm going to take the x minus 4, set that equal to 0, and that gives me x equals 4. So my intercept would be at 4, 0. And then I am going to take the x plus 2 and set that equal to 0. When I subtract, I get -2, so that would be -2, 0. And that would be our two x-intercepts. Now this second fraction, or second example, this is what we call a special case. And it's a special case because it is not a single fraction. Keyword is single fraction. There is something going on after the fraction. So that -2, this -2 changes everything. Now we also know by definition, to find your x-intercept, the definition of the x-intercept is the x value when y is 0. So when we run into this special case, we're going to have to approach it a different way. So what I'm going to do is set this equal to 0. So I have 0, and that equals 4 over x plus 3, and then -2. So I'm going to go ahead and solve this for x. First, I'm going to begin by adding 2 to both sides. So what that's going to give me is 2 equals 4 over x plus 3. Now I'm going to just write this as a proportion, which is optional, but I find that some students like to make both sides a proportion as they cross multiply. But I'm multiplying these two sides, and I'm also multiplying these two sides, the opposite two sides. So these two sides. So when I do that, I get 2 times x plus 3 equals 4 times 1. And again, pause the video to see if you're going to get the same answer that I get. So if you got -1, 0 as your answer, you are correct. That would be our x-intercept. And that covers example 1. So the next thing we're going to look at is domain. How do we determine the domain? Remember, domain, there's 2 red lights. One is a square root, the other one is an x in our denominator. So here when I'm finding the domain, the focus is on my denominator. So we have had a lot of practice with this. So what I'm going to do is simply factor my denominator. And when I factor that down, I get two numbers that multiply to 15 and add to 8 is 3 and 5, which means that x cannot equal -3 or -5. So when I'm writing this in interval notation, okay, keep in mind we're going from -infinity to infinity. I'm saying that I can use any number except -5 and -3. So essentially what I have is 3 parts of my domain that I have broken it into. I have this first portion, which would be -infinity to -5, union, and then I have my middle portion, which is in between -5 and -3. And then lastly, I have the far right, which is -3 to infinity. And that would be our domain. The next thing we're going to talk about is vertical asymptotes. Now, we've already talked about discontinuities in this chapter. We've talked about the 3. There's an infinite, there's a removable, and there is a jump. So the infinite discontinuity comes into play from your denominator also. Except the difference is I'm going to write it as an equation, not an ordered pair. So focusing only on my denominator, when I set this equal to 0, subtract the 1 and divide by 2, I get x equals -1/2. That is my vertical asymptote. And what that means is at that point in the graph, it is going to either shoot up to infinity or shoot down to -infinity. That is where where we will draw, because we are going to graph these later on. That is where we will draw a dashed line to show that the graph cannot cross that. Now you can have more than one. For the second example, notice that we have a quadratic. So when I factor this down, two numbers that multiply to be 15 and add to -2. That's actually an error. Sorry, let me fix that. That should be two numbers that multiply to give you -15 and add to -2. Sorry. Okay, so the two numbers would be -5 and +3. So that means that for this equation, this function, we have 2. So just to kind of sketch it out a little bit so you can kind of see. And again, we will graph these. That just means that we have to draw in a wall at +5, and it's also going to be discontinuous at -3. And the kind of discontinuity that's going to occur is an infinite. And we have to graph it to see if it's going to go up or down. So we can have, two different ones. This is just a sketch of a possibility, but not saying this is what it looks like. But again, just notice that at both places, the graph on that wall is approaching either positive or negative infinity. And let's talk about the next discontinuity, which is a hole in the graph. All right, when do we see a hole in the graph? We see a hole when you can cancel a factor, okay? So when I look at the numerator, The two numbers that would multiply to give me a positive 8 and add to a negative 6 would be negative 2 and negative 4. And in my denominator, two numbers that multiply to give you negative 12, but add to a positive 4 would be 6 and 2. And the 6 is positive and the 2 is negative. So the common factor that is in top and bottom, which would cancel, is x minus 2, okay? Because it cancels, what that is going to create is a hole in the graph. So this would be the function that we would graph, but our hole, okay, so we have a hole at, and it'll be, we take the factor that cancels, which is x minus 2. So we have x equals 2. That's the x value of the hole. And then to find the y value, I'm going to substitute that positive 2 into the equation that we have remaining. So I would have 2 minus 4, so y equals 2 minus 4 over 2 plus 6, which is negative 2 over 8. And we know we always reduce a fraction. So that means that on the graph, at this point, there was going to be an open circle at 2 and negative 1/4. All right, now let's talk about our asymptotes. So there are 3 different types of asymptotes that we can have. We can have a horizontal asymptote. We can have a slant asymptote. And the slant looks like this. Okay, so let's talk about when we know when we're going to have each one. If the leading coefficient is equal to each other. So when I look at the leading coefficient, what I'm really talking about is the degree. So if the degree for top and bottom are the same. So the degree, so we're looking at the degree at the top and bottom. If the degree is equal, if it's equal, then that means that my horizontal asymptote is going to just be a ratio of the leading coefficients. So in this example, they're both a second degree, so they're equal. So to find my horizontal asymptote, it would simply be y equals 3/4. And then again, here we go with our special case, because this one has a -4. So we're still going to start at the same. Notice they both have an equal degree, but I still need to divide my leading coefficients. So that would be y equals, and I'm going to take the 3/1. So we still do 3/1. But now we have to tack on this -4, which is why it's special. So I have a horizontal asymptote at y equals 3 minus 4, which is y equals -1. So both of these would have a horizontal, a straight horizontal asymptote, because they are equal degree and we're dividing the leading coefficients. If there is a number that's tacked onto the end, like a -3 or a +3, we do have to take that into account. So for example, going back to the first one, if this -3 was there, I would have to subtract the 3. So we can't ignore that if there is a term after that one fraction. The next one is bottom heavy. Now, bottom heavy is the easiest to find, because if you have a rational function where your degree is higher on the bottom. That's why it's called bottom heavy, because you have a higher degree in the denominator. So I'm going to write that higher degree in denominator. Now, when that happens, we just know that our horizontal asymptote will be at y equals 0. So looking at our first example, and remember, as you're watching this, you can always pause. Hopefully you're pausing as I'm going through it so you can copy down the examples. But there's a 1 here and a 2. 2 is higher than 1. So my horizontal asymptote is just simply going to be y equals 0. So on my graph, on the x-axis, because that's where y is equal to 0, that is where we have an asymptote. Anytime it's bottom heavy. So now we have a special case again, because the numerator has a degree of 0. There's an invisible x to the power of 0. And then there's a 1 in the bottom, okay? It's higher in the bottom. So my horizontal asymptote, we're still going to start it off at y equals 0. But we can't ignore this minus 4. So we have to bring that down and do something with it. So what we're going to do whenever it is that special case, if it's a minus a number or add a number, is we're just going to subtract that or add it to the 0. So in this example, we would have a horizontal asymptote at y equals -4. And then our last example for today is, what if it's top heavy? Well, when it's top heavy, again, that means you have a higher degree in the top. So the higher degree is in the numerator. We have to do synthetic division. So let me go back and recap. There's 3 options. Either you're going to have, let me go back. So either they're going to be the same degree top and bottom, which means they're equal, and we simply divide the leading coefficient. So either it's equal or it's higher on the bottom, and when that happens, it's just y equals 0, unless it's a special case and you have to add or subtract the number. And then your last option would be higher in the top. So when that happens, we have to do synthetic division. And the steps to synthetic division will be, you're going to look at and determine where is your vertical asymptote. Remember, your denominator determines your vertical asymptote. So I'm going to take that x plus 2, set that equal to 0, and I get x equals -2. That is the number that I'm putting on the outside here. And then I'm going to look at my numerator and only write the coefficients. So that would be a 1, a 1, 1, 1, and 3. And our steps to doing synthetic division does not change. We're still going to drop down that first number. When I multiply the -2 times 1, I get -2. And then I add these together, and I get -1. We can actually stop there. The third number is irrelevant in this example. These 2 numbers represent the slope, which is m, and the y-intercept, which is b, of the slant. So when it's a slant, we have an equation also. And for this one, the equation will be, keeping in mind the format for a linear equation is y equals mx plus b. So my equation will be y equals, and then it's 1x, and my y-intercept is -1. So just because we have time, I'm going to go back through and just recap what we talked about. First thing we talked about was our intercepts. more specifically the x-intercept. Now we will talk about y-intercept a little bit later. We'll talk about that. We'll talk about the y-intercept when we start graphing these in class. But the y-intercept, you would set the x equal to 0. But we focused on the x-intercepts, which comes from the numerator. So remember, x-intercept comes from numerator. We wrote that as an ordered pair. And then we looked at what to do if it's a special case. That's where we have to set the whole thing equal to 0 and solve it. The next thing we talked about is domain. Remember, we can't divide by 0. So we had to determine what numbers from positive infinity to negative infinity to exclude, and we had to write our domain. After domain, we talked about vertical asymptotes, which also come from the denominator, but it's written as an equation. So this would be my vertical asymptote, but if it asked me for the domain, it would be negative infinity to negative 1/2 union negative 1/2 to positive infinity. But it didn't ask that. But just remember, vertical asymptote always comes from the denominator, and you don't write it as an equation. You write it as x equals whatever that is. And you can have more than one. And the second one here, notice we had 2 vertical asymptotes. After we talked about asymptotes, we then moved on to removable discontinuities. And that occurs when you can cancel a factor. I'm going to write that. Whenever you can cancel a factor. Lastly, we talked about the end behavior. If it's equal, we divide our leading coefficients. If it's higher at the bottom, it's equal to 0. And if it's higher on top, we need to do synthetic division.